Mercury, the smallest planet in the solar system, harbors a geological feature that rivals Earth's most impressive structures. Olympus Rupes, a massive tectonic fault that stretches for hundreds of kilometers, slicing through the planet's crust. This formation is not just a simple crack, it's a gigantic scarp where one part of the crust overrides the other. What's most astonishing about Olympus Rupes is the fact that Mercury has been shrinking over time, causing the planet's crust to compress, creating these massive fractures. Over billions of years, Mercury has contracted by about 7 kilometers in radius, and Olympus Rupes is one of the most visible signs of this process. The structure rises up to 3 kilometers high, like a giant wall emerging from the ground, but this isn't the result of an impact or volcanism. Instead, it's caused by internal forces compressing the planet's core. It's as though Mercury has been gradually squeezed since its formation. This phenomenon is rare among planets. While some planets show localized expansions and contractions, Mercury shows evidence of global shrinkage, with multiple similar faults spread across its surface. Olympus Rupes is just the most dramatic, standing out not only for its size, but also for its sharp, straight edges. Images from NASA's MESSENGER probe have mapped these formations with remarkable precision. The clarity of the fracture is astounding, with its sharp edge casting long shadows as sunlight strikes it at an angle. This suggests the fault is relatively recent, at least by planetary standards. For a world as ancient as Mercury, the existence of such a well-preserved fault raises intriguing questions about its internal dynamics. Once thought to be geologically dead, Mercury might still have residual tectonic activity that keeps these fractures intact much longer than expected. Another mystery revolves around what lies beneath Olympus Rupes. Some theories suggest that Mercury's core could still be partially liquid, which contradicts traditional ideas about planetary cooling. If this is the case, it could explain not just the shrinkage, but also the planet's magnetic field. The contrast between Mercury's barren, dry surface and these signs of internal activity transforms it into a natural laboratory, providing valuable insights into the thermal and structural history of a world once thought unremarkable. Visually, Olympus Rupes stands as a solitary wall cutting through a barren landscape. The lack of atmosphere on Mercury has preserved the fault almost perfectly, with no erosion or landslides to obscure it. The formation has a frozen-in-time quality, as if it just appeared. When compared to Earth's faults, like the San Andreas, the difference is striking. On Earth, plates slide past each other. On Mercury, however, the plates sink beneath one another, a much more radical form of tectonism. The orientation of the fault suggests a global pattern of contraction, not just an isolated event. Olympus Rupes is a part of a broader system of fractures that indicate a nearly spherical compression of the planet. This could mean that Mercury is still shrinking, albeit slowly, which makes the planet more active than we previously thought. Each rise in the fault serves as a reminder that even the oldest, seemingly stagnant bodies in the solar system have stories to tell. Instead of earthquakes, Mercury endures tectonic shrinkage, and each of these structures is a record of that ongoing process. Olympus Rupes in particular stands as one of the most dramatic geological features on any planet, challenging our understanding of planetary geology. Mimas, one of Saturn's smallest moons, was once considered geologically inactive. With a mere 396 kilometers in diameter and a heavily cratered surface, it seemed like a cold, lifeless rock drifting through space. However, recent discoveries from the Cassini mission have revealed something unexpected: subtle oscillations in Mimas's orbit and rotation, suggesting something is shifting beneath the surface. These fluctuations point to the possibility of a hidden subsurface ocean, an idea no one had anticipated for such an unassuming moon. Mimas has none of the usual signs of internal activity that other moons like Enceladus display. It doesn't eject visible plumes of ice, nor does it have youthful, geologically active surfaces. Yet its orbital behavior indicates the presence of a liquid layer beneath its icy crust. This suggests that Mimas might harbor an ocean completely sealed off from the surface, hidden beneath tens of kilometers of ice. The moon's interior could remain warm due to tidal forces from Saturn, which stretch and compress Mimas as it orbits the gas giant. This friction could be enough to maintain the ocean in a liquid state. Recent models suggest that even small bodies like Mimas can retain heat and preserve liquid water for billions of years under the right conditions. This raises the intriguing possibility that Mimas could be a potential candidate for microbial life, despite its small size and lack of apparent surface activity. The discovery of a hidden ocean beneath its icy shell would place Mimas on the shortlist of moons that could harbor life, alongside more prominent candidates like Enceladus. Scientists are actively looking for more concrete evidence of this subsurface ocean. Potential clues include detecting microscopic plumes or gravitational anomalies in future missions. Until then, the possibility that Mimas has a hidden active ocean remains one of the most exciting mysteries in the solar system. If confirmed, Mimas would become the smallest moon known to harbor internal liquid water, a remarkable discovery for such an inconspicuous celestial body. While the moon's surface may resemble the Death Star from Star Wars, we now know that the real mystery lies beneath its icy exterior. Planetary science is constantly challenging its assumptions, and one question has surfaced. If Mimas has an ocean beneath its surface, how many other dead moons could also harbor hidden oceans? This possibility significantly widens the scope of worlds that might support life. Venus, with its dense clouds of sulfuric acid, has always been difficult to study directly. However, data from the MESSENGER mission has revealed intriguing signals from specific regions of Venus's surface, suggesting the presence of glassy materials. These signals indicate highly smooth surfaces composed of volcanic glass. The glass deposits are located in elevated regions where ancient volcanic eruptions likely spread molten lava that rapidly cooled upon contact with the planet's thick atmosphere. On Earth, volcanic glass forms quickly in lava flows, but Venus's extreme heat and pressure make the process much more complicated. The formation of volcanic glass on Venus requires a precise balance of temperature, chemical composition, and eruptive conditions. In certain highland areas called tesserae, the reflections observed point to materials similar to obsidian, which could indicate explosive volcanic activity, challenging the previously held belief that Venus only experiences slow volcanic eruptions. This discovery suggests that Venus may have a more complex geologic history than we thought. The presence of volcanic glass points to significant variations within Venus's interior, altering how we understand the planet's surface composition. This also impacts our study of Venus's climate and thermal evolution, as glassy materials reflect radiation differently than basaltic surfaces. Recent radar maps have strengthened the idea that Venus may have vast fields of glassy rock hidden beneath its thick clouds. The challenge lies in the limitations of current technology, which can detect reflections but cannot yet confirm the composition of these materials without in situ measurements. Future missions, like Veritatis and Envision, are set to explore these areas further. These regions, where topography, reflectivity, and emissivity converge, are prime candidates for containing volcanic glass, potentially revealing more about Venus's geological past and the intensity of past thermal activity. Triton, Neptune's largest moon, is one of the most fascinating and enigmatic bodies in our solar system. Its retrograde orbit suggests that Triton was once a dwarf planet captured by Neptune's gravity, but what truly stunned scientists were the active nitrogen geysers erupting from Triton's icy surface. These geysers are not composed of water, but rather a mixture of gaseous nitrogen and dark particles that are ejected kilometers into the sky. First observed by Voyager 2 in 1989, these plumes left long dark streaks across Triton's icy surface. The dark particles fall back to the surface, forming trails that suggest sustained activity. This behavior points to a thermal source beneath the icy crust, caused by explosive sublimation. When sunlight penetrates Triton's surface, it heats the nitrogen ice beneath. As the gas builds up, pressure increases until the crust ruptures, releasing vertical jets of nitrogen gas and dark dust. These jets can reach impressive heights, with some reaching 8 kilometers, almost as high as Mount Everest. What makes Triton's geysers even more interesting is that they do not emerge from visible fractures or fissures, unlike those on moons like Enceladus or Europa. Instead, the geysers erupt from flat terrain, indicating a different type of cryogeological activity that's less dependent on tectonic structures. The dark particles in these geysers appear to be carbon-rich dust mixed with nitrogen ice, providing a stark contrast against the moon's bright surface. This unique surface pattern offers scientists a new way to study Triton's climate and its internal processes. Triton's crust also displays a cantaloupe terrain pattern with rough, rounded depressions that suggest deformation caused by internal pressures. These plumes, which are aligned in longitudinal bands, further suggest some kind of thermal or geographic control over their formation. This provides valuable insight into the Moon's internal activity and offers clues about where new geysers might appear in future observations. Triton's continued geyser activity suggests the Moon still retains some internal heat, making it a high-priority target for future missions to the Neptune system. Uranus has long puzzled scientists due to its extreme axial tilt and the odd behavior of its magnetic field. Unlike Earth's magnetic field, which aligns closely with its rotational axis, Uranus's magnetic field is tilted by 59 degrees and offset from the planet's center. This creates a lopsided magnetosphere that tumbles through space as the planet rotates, resulting in a chaotic and asymmetrical magnetic environment unlike any other in the solar system. The Voyager 2 spacecraft, which flew past Uranus in 1986, mapped the planet's magnetic field. The data revealed magnetic lines that spiral and loop in unexpected directions, forming regions of intense distortion. Uranus's magnetic poles shift dramatically as the planet rotates, causing the north and south magnetic poles to constantly change their position in space. Recent studies suggest that the planet's magnetic field is generated in a thin shell of ionic fluid closer to the surface, rather than deep within a central core, as seen on Earth. This could explain the field's unusual behavior and lack of symmetry. The nature of Uranus's magnetic field continues to be a source of fascination, raising more questions about how the planet's interior functions. The unusual rotation of Uranus, tilted nearly on its side, adds another layer of complexity, making the planet's magnetic behavior both unpredictable and difficult to model. One consequence of this magnetic distortion is the erratic location of Uranus's auroras. Unlike the relatively stable auroras on Earth, which are confined to the poles, Uranus's auroras can appear far from its geographic poles and in unexpected shapes. These auroras are created by interactions with the solar wind, which enters the planet's tilted magnetosphere at unpredictable angles. This causes bursts of electromagnetic activity in locations that defy normal planetary behavior. The skewed magnetic field also impacts how Uranus's atmosphere is protected from solar radiation. Because the magnetosphere is tilted and offset, some parts of the planet's upper atmosphere are more exposed to the sun's radiation than others. This uneven shielding could have a significant effect on the distribution of charged particles and may even alter the chemical makeup of the planet's outer layers. Scientists believe this uneven exposure may be one of the reasons why Uranus appears surprisingly featureless in visible light. Magnetospheric models show that as Uranus rotates, its magnetic poles trace wide circular paths in space. This movement generates complex magnetic storms that build up and dissipate with each rotation, changing how the planet interacts with the solar wind. Unlike Earth, which has a steady magnetic tail, Uranus has a warped spiraling tail that twists in a corkscrew pattern. Additionally, the magnetic poles of Uranus do not align with the planet's surface features, as the source of the magnetic field is not centered in the planet. This creates challenges for spacecraft navigation and communication near the planet, as the magnetic field is difficult to predict and map. The Uranus's magnetic field remains a subject of intense study, as it offers valuable insights into the magnetic behavior of ice giants and their unusual internal structures. The planet's misaligned magnetic axis is not just an anomaly, but challenges scientists to rethink how magnetic fields are generated and maintained in rotating, fluid bodies. Future missions, including those involving the James Webb Space Telescope, will provide more data that may help refine our understanding of Uranus's magnetic behavior. These investigations could reveal whether Uranus's magnetic field is stable over long periods, or if it is in the process of shifting or even reversing. For now, Uranus remains one of the most intriguing and unpredictable magnetic environments ever observed in the solar system. Mars, known for its vast deserts, towering volcanoes and icy poles, also harbors a unique and often overlooked atmospheric phenomenon, carbon dioxide snowfall. During the Martian winter, the planet's temperatures drop so low that carbon dioxide in the atmosphere freezes, falling as snow at the poles. Unlike Earth's water ice, this snow consists of dry ice, solid CO2, that settles in fine, almost invisible layers on the ground. This phenomenon mainly occurs at the southern polar cap, where winter darkness and minimal sunlight cause temperatures to plummet below -25 degrees Celsius. At these frigid temperatures, atmospheric CO2 condenses into ice crystals and falls from the atmosphere. Orbiters equipped with infrared and radar instruments have confirmed the presence of this seasonal CO2 frost, which blankets the polar regions during the winter months. However, this snow doesn't fall in large flakes. Instead, it falls as tiny crystals that resemble fine dust. These microscopic particles accumulate over time, creating a reflective surface that increases the planet's albedo. The seasonal buildup of dry ice can reach up to a meter thick, significantly altering the reflectivity of the surface and influencing local weather patterns. One fascinating aspect of CO2 snowfall is its role in reshaping Mars's polar landscape. As spring arrives and sunlight returns, the dry ice begins to sublimate back into gas, sometimes in a violent manner. This process can cause cracks, jets, and even surface erosion. Some features near the South Pole, such as dark fans and spider-like patterns, are created by the rapid sublimation of CO2 beneath the surface. As sunlight penetrates the translucent dry ice, it warms the ground underneath. Trapped gas builds up pressure until it bursts through the ice, sending dust and sand into the air in geyser-like plumes. These plumes settle around the eruption site, creating the distinctive spiderweb patterns seen on the surface. Unlike water-based snow, CO2 snow cannot last through the Martian summer. As temperatures rise, the dry ice evaporates completely, making this phenomenon strictly seasonal. The process repeats each Martian year, offering scientists valuable insight into Mars's volatile climate cycles. The southern pole, in particular, experiences the most dramatic changes due to its colder temperatures and unique topography, making it the primary location for this weather event. Recent observations from the Mars Reconnaissance Orbiter have refined our understanding of CO2 snowfall, providing detailed measurements of the timing and scale of these snowfalls. Instruments like the Mars Climate Sounder detect not only surface frost but also airborne snow particles, confirming that the snow actually falls from the sky rather than merely forming on the ground. This has confirmed that Mars does indeed experience a true form of snowfall, albeit one unlike anything seen on Earth. The build-up and eventual sublimation of CO2 snow also cause subtle shifts in the planet's atmospheric pressure. As the gas returns to the atmosphere in spring, the total pressure increases slightly, affecting wind and weather conditions across Mars. This dynamic cycle of CO2 snow is essential for understanding Martian climate patterns, especially when planning future robotic or human missions. Changes in surface reflectivity, atmospheric pressure, and local weather conditions could all impact landing strategies and energy management. Even though CO2 snowfall is invisible to the naked eye, it plays a critical role in shaping the Martian landscape, revealing the planet's capacity for active seasonal changes. As each Martian year passes, this silent snowfall continues to reshape the red planet in ways that are only just beginning to be understood. Uranus, the ice giant, holds mysteries beyond its icy exterior. One of the most intriguing is the behavior of its auroras. These glowing phenomena, which we typically associate with solar winds interacting with a planet's magnetic field, behave in unusual ways on Uranus. The intensity and frequency of the auroras don't always match changes in solar activity, hinting that there's something deeper at play inside the planet itself. This suggests that Uranus's inner workings might play a significant role in shaping the auroras we see. The planet's magnetic field remains a puzzle. Is it stable, or does it fluctuate over geological timescales? These questions remain unanswered, but telescopes like Hubble and XMM Newton are giving us the chance to study Uranus more closely during periods of strong solar wind. During these opportunities, researchers are able to observe brief flashes of auroral energy, each one adding another piece to our growing understanding of Uranus's magnetic personality. In the future, missions to Uranus could include radio frequency instruments that would allow us to track these auroras in real time. Unlike traditional imaging methods, radio data can pass through cloud cover and provide continuous monitoring of magnetic activity. This technology could revolutionize our understanding of how complex magnetic geometries influence atmospheric phenomena. Uranus's auroras are unique in that they are detected primarily through their radio emissions. This elusive characteristic highlights how much remains hidden beneath the surface of planetary atmospheres, even when the conditions for activity are clearly present. The auroras are not bright and flashy. Instead, they softly trace magnetic currents across the planet's dark blue skies. Next, let's turn our attention to Saturn's moon, Opatus. This moon is unlike any other in the solar system, primarily due to its unusual color contrast. One hemisphere is as dark as coal, while the other gleams as bright as fresh snow. This stark division creates the appearance of a yin-yang moon, as if painted by two distinct forces. For decades, scientists have puzzled over the cause of this color difference, but the Cassini spacecraft provided us with important new clues. The darker hemisphere, named Cassini-Rayo, is coated in a thin layer of carbon-rich material. This coating likely originates from external sources, perhaps from dust produced by Saturn's outer moons, or retrograde satellites like Phoebe. As Opatus travels through this particle cloud, the material preferentially accumulates on the moon's leading hemisphere, the one that faces the direction of its orbital motion. Once this dark material is deposited, it absorbs more sunlight, which in turn causes the surface to heat up. The heat causes ice on the dark side to sublimate and recondense on the bright hemisphere. Over time, this process strengthens the contrast between the two sides, causing the dark side to become darker and the light side to become brighter. However, the color contrast is only part of Opatus's mystery. The moon also boasts an extraordinary equatorial ridge that stretches halfway around its circumference. This ridge, which rises up to 20 kilometers high in some areas, is unlike anything seen on other moons or planets. Scientists have proposed several theories to explain this ridge's formation. One idea is that it could be the remnants of a collapsed ring system, debris that once orbited Opatus and eventually fell to its equator. Another possibility is that the ridge formed from tectonic processes when Opatus was still warm and partially molten. Despite many theories, no single explanation accounts for all the features of the ridge, including its varying height and discontinuities. The ridge's highly eroded surface suggests that it is ancient, possibly billions of years old. Despite its age, it remains one of the most striking features of any moon in the solar system. The ridge divides Opatus in a way that adds to its already peculiar visual and geological characteristics. Measurements of gravity and shape suggest that Opatus once rotated much faster, and the ridge could be a remnant from this earlier, faster rotating phase. If this theory is correct, the ridge is not just an oddity, it's a fossil from a different era of the moon's dynamic history. Cassini's flybys revealed high-resolution images of the ridge, showing impact craters and landslides that further shaped its profile. Some parts of the ridge appear almost artificially symmetrical, adding to the moon's mystique. However, there's no sign of tectonic movement or resurfacing activity, indicating that Opatus is a frozen, dormant world. The combination of its color dichotomy and massive ridge makes Opatus a geological outlier. While most moons are shaped by tidal forces, Opatus seems to defy easy classification, and its anomalies point to the incredible variety of moon formation histories across the outer solar system. On Mars, there is a different type of geological wonder, the Korolev crater, located in the northern lowlands. This 82 kilometers wide basin holds something unexpected, a permanent deposit of water ice. Unlike the seasonal frost that comes and goes with the changing seasons, this ice remains year-round. What keeps it so stable is a natural atmospheric phenomenon known as a cold trap. This cold trap allows the ice to persist in a stable state, unaffected by seasonal changes or shifts in the Martian atmosphere. The ice inside Korolev is over 1.8 kilometers thick, holding a staggering amount of frozen water, roughly equivalent to all of Lake Ontario. What makes Korolev even more unique is how the ice is preserved. The air above the ice is colder than the air outside the crater, which creates a natural cold layer that prevents the ice from turning into gas. This self-sustaining cold trap works even under Mars's thin atmosphere, ensuring that the ice hasn't sublimed over the course of thousands, if not millions, of years. Mars orbiters, like Mars Express, have captured stunning images of the crater's frozen interior. The contrast between the ice and the surrounding red dust creates striking visuals, helping scientists map the Martian landscape. Radar instruments have confirmed that the ice is almost entirely water, not carbon dioxide or regolith, providing valuable insights into the planet's climate history. The impact that formed Korolev played a crucial role in creating the crater's depth, which is essential for trapping cold air. Unlike many Martian craters which erode or fill with sediment, Korolev has remained relatively intact, allowing ice to accumulate undisturbed. For geologists, Korolev represents a time capsule of Martian climate. The layers of ice inside the crater may preserve a record of seasonal or orbital climate changes, much like Earth's ice cores. Studying these layers could reveal critical data about the planet's past atmosphere, including shifts in tilt and solar radiation. For future exploration, Korolev is a prime target for resource utilization. The accessible water ice could serve as a crucial resource for long-term human missions to Mars, providing water for drinking, fuel, and other essential needs. Pan, one of Saturn's smaller moons, is unlike anything else in the solar system. It has a unique ridge that stretches evenly around its equator, rising several kilometers in places, giving it a distinctive shape. This feature makes Pan resemble an object designed for rotation, but its appearance is shaped by the moon's weak gravity and the continuous influx of debris from Saturn's rings. The debris settles at the moon's equator where the centrifugal force is weakest, gradually forming the ridge we see today. Pan plays an important role in shaping Saturn's rings. Its gravitational pull affects the particles around it, creating a gap in the rings called the Uncke gap. As Pan orbits Saturn, it disturbs nearby particles, creating a clear path through the dense rings. But it does more than just create this visible gap. The moon's orbit also produces subtle waves and ripples in the surrounding ring material, adding complexity to the ring system. Despite being small, Pan's surface is riddled with craters. Some of these impacts may have caused the redistribution of surface material, which could explain how the ridge developed over time. Pan's weak gravity allows debris from collisions to fall back onto the moon's equator, reinforcing the ridge further. But Pan's impact on the rings doesn't stop there. The moon's orbit causes the edges of the gap to oscillate, creating spiral density waves that radiate outward. These waves help scientists understand more about both Pan and the particles in Saturn's rings, offering valuable insights into how disks behave in space. Pan's orbit is almost perfectly circular, and it orbits very close to Saturn, completing a full revolution in less than 14 hours. Despite this, Pan stays stable thanks to its position in a resonance zone, a safe area within Saturn's rings. This makes Pan a rare example of a small moon that thrives in such a dynamic environment. It's believed to be composed mainly of water ice, similar to other small moons and ring particles, and its bright surface makes it easy to spot against the dark backdrop of Saturn's rings. Spectral data shows that Pan's surface is almost free of darker carbon-rich materials. What makes Pan especially interesting is that it's the only known moon to combine its size, shape, and position within the rings. Its presence proves that moons can not only form within rings, but can also persist and evolve, playing a significant role in shaping their environment. This challenges our earlier assumptions that moons and rings are always separate. Pan is often referred to as a ring shepherd, although it doesn't control the particles directly. Instead, its gravity subtly influences the particles, leaving a lasting impact on the structure of Saturn's rings. Next, let's move to another fascinating moon, Enceladus. This moon, one of Saturn's mid-sized satellites, hides a powerful secret beneath its icy surface, a global subsurface ocean. The ocean reveals itself dramatically at Enceladus's south pole, where massive fissures, nicknamed tiger stripes, constantly shoot out plumes of water, vapor, and ice. But what makes this even more remarkable is the presence of swirling currents beneath the surface. These hidden whirlpools, driven by tidal forces and temperature differences, are crucial for circulating heat and organic material throughout the ocean. Unlike the surface currents we see on Earth, these whirlpools are found deep kilometers of ice. They are caused by Saturn's immense gravitational pull, which stretches and heats Enceladus as it orbits the planet. This internal friction generates localized convection cells that create swirling water currents beneath the tiger stripes. These currents help move warm water towards the fissures, allowing it to escape as vapor and fine ice particles. Without this internal stirring, the ocean would likely freeze from the top down. The discovery of these currents has profound implications for Enceladus's potential habitability. The movement of water could support chemical gradients necessary for complex chemistry, possibly sustaining microbial life. Data from Cassini has shown variations in heat emissions across the tiger stripes, with some areas being consistently warmer than others. These differences suggest that the warmth comes from the moving water below the surface, which channels heat from deeper layers to the upper crust. The plumes that erupt from Enceladus also contain organic compounds, salts and silica nanograins, all of which require heat and water-rock interactions that could occur within the rotating convective cells. Gravitational studies of Enceladus's shape reveal that it has a thin outer shell and a liquid interior, confirming the presence of dynamic currents. These tidal forces are strongest at the poles, which align with the areas of greatest activity at the South Pole. Simulations suggest that small differences in the Moon's crust or seafloor topography could cause the water to form vortex-like structures, which influence the shape and activity of the fissures. These interactions create a feedback loop, where internal water currents shape the surface features and keep the plumes active. The exact structure of these whirlpools is still theoretical, but computer simulations show that they are likely to form under a wide range of thermal and gravitational conditions. Future missions could confirm their presence through seismology or advanced gravitational measurements, allowing scientists to map the interior of Enceladus in even greater detail. Understanding these subsurface flows is crucial for assessing the Moon's habitability. These currents could distribute nutrients and energy throughout the ocean, preventing stagnation and fostering environments that could support life. Enceladus's south pole isn't just leaking, it's pulsing, breathing in time with the tidal forces, offering a glimpse into the complex dynamics of its hidden ocean. Measurements from occultations provide incredibly detailed data, revealing more about the shape and size of objects than any telescope image ever could. These observations allow scientists to refine orbital calculations while also tracking subtle changes in the spin and mass distribution of distant worlds. In the case of Hamaha, a mysterious object in the outer solar system, such measurements have revealed fascinating insights. The object's unique shape, resembling an elongated rugby ball, is thought to be the result of a past collision. This catastrophic event may have scattered debris, giving rise to both Hamaha's two moons and its ring system, linking the object's current state to a violent history. The eccentric shape of Hamaha, with its rapidly spinning body, serves as a preserved record of its dynamic past in the outer solar system. The spin of Hamaha affects not only its appearance but also the distribution of gravity across its surface. The equator, due to centrifugal forces, experiences weaker gravity, making it easier for surface particles to escape or migrate. This effect may influence the texture and brightness distribution of the Moon's icy surface, and even play a role in the long-term evolution of its crust. Though far from Earth and invisible to the naked eye, Hamaha continues to be studied through indirect methods like infrared spectroscopy and occultation tracking. These techniques offer surprising clarity about the Moon's shape, rotation, and even its ring system. The combination of Hamaha's fast spin, its distorted shape, and subtle brightness variations make it one of the most exotic dwarf planets discovered in the outer solar system. Hamaha's shadow, cast across space like a cosmic fingerprint, provides more than just a silhouette. It is a spatial signature of a world bent by rapid rotation and shaped by collision. With each occultation event, scientists gather more information, getting a sharper picture of this fast-spinning enigma on the outer edge of the Sun's influence. Next, we venture to Neptune, a planet of deep blues and extreme weather. Among its many atmospheric phenomena, one of the most striking is the Serpent Storm. First captured by the Hubble Space Telescope, this massive twisting cloud system stretches across Neptune's atmosphere like a ribbon, dark and sinuous in form. Unlike the typical great dark spots that appear and fade over time, this storm retains its serpentine shape, composed of multiple coils visible along its length. The storm was first spotted in the mid-2010 sinks, and since then it has reappeared, indicating a recurring atmospheric pattern. Spanning thousands of kilometers, the storm consists of both bright and dark cloud layers, which are likely made of methane ice crystals, along with denser, deeper material. The sharp contrast between these layers points to turbulent mixing, where gases from different altitudes are interacting violently. This twisting, snake-like storm is driven by Neptune's powerful jet streams, which rip through the upper atmosphere at speeds greater than 1,600 kilometers per hour. These winds stretch the clouds, pulling them into long, curved bands. The storm's elongated shape is a result of a battle between vertical convection, which rises from deep within the planet, and horizontal wind shear, which stretches the clouds in the upper layers. Some observations show that the storm's coils seem to spiral with multiple loops, rotating independently within a larger arc. This suggests that the serpent storm is not just one entity but a collection of interacting systems. The storm's appearance changes depending on the wavelength of light. In ultraviolet and infrared wavelengths, the storm's brightness varies, indicating differences in particle size and altitude. The brighter areas may be higher altitude clouds made of methane, while the darker zones likely represent deeper cloud layers or larger, more absorbing particles. These differences help scientists model how energy and material move through Neptune's dense, cold atmosphere. Although the serpent storm is transient, sometimes shifting latitude or dissipating entirely within a few years, its recurring nature suggests that an underlying pattern exists, possibly related to seasonal changes or cycles of convection within Neptune's interior. The serpent storm has become one of the most studied features of Neptune's atmosphere, with researchers tracking it closely due to the challenges it presents for remote sensing. Each time the storm appears, it provides a narrow observational window into the dynamic weather systems of Neptune. One of the most intriguing aspects of the storm is its interaction with Neptune's polar haze. In some images, the serpent storm seems to brush against the high-latitude band of clouds, creating ripple-like distortions in the haze. These subtle deformations hint at the layered nature of Neptune's atmosphere, where vertical motion is constrained much like Earth's troposphere. The serpent storm provides a unique laboratory for studying fluid dynamics under extreme planetary conditions. Modeling the storm's behavior requires accounting for Neptune's rapid rotation, weak sunlight, and exotic chemistry. Understanding these atmospheric processes not only helps us learn more about Neptune, but also aids in our study of exoplanets with similar mass and temperature. While the serpent storm may not last forever, its striking appearance and complex structure continue to captivate scientists and the public alike. It's a reminder that even the most distant planets in our solar system are full of surprises shaped by chaotic systems that never fully settle. Now let's turn our attention to Uranus and its lesser-known moon, Ariel. Though it is one of Uranus's 5 major moons, Ariel is rarely discussed in detail. Its quiet reputation belies the dramatic landscape that exists beneath its icy surface. The moon is covered in deep canyons, fault valleys, and fractured plains, geological features that rival even Earth's Grand Canyon. These formations were first captured by Voyager 2 in 1986, revealing a young and surprisingly active landscape shaped by internal forces. The most notable features are the canyons, long and narrow cracks that cut across Ariel's icy crust for hundreds of kilometers. Some of these canyons plunge as deep as several kilometers, indicating significant tectonic stretching. Unlike other Uranian moons which are covered in older cratered surfaces, Ariel's surface shows evidence of resurfacing. Smooth plains appear to have flooded older landscapes, possibly due to cryovolcanism, ice-rich material erupting from below the surface. These resurfaced areas are relatively young in planetary terms, pointing to a history of internal activity. Spectral data suggests that Ariel's surface is a mix of water ice and silicate materials, with the possibility of ammonia compounds present as well. This composition suggests that Ariel may have subsurface reservoirs of water that were once active and may have reached the surface during past eruptions. Ariel also displays tectonic patterns, with grooves and ridges aligned in parallel. These features are similar to those seen on moons like Ganymede or Europa, and they suggest tectonic stress caused by orbital forces. While Uranus exerts tidal forces on Ariel, they are much weaker than the forces Jupiter exerts on Ganymede, making Ariel's tectonics more subtle but still significant. These deep canyons are ideal for studying Ariel's geological history, as the exposed ice and rock layers act as a vertical record of its surface evolution. Despite its potential, Ariel remains largely unexplored since Voyager 2's flyby. Only a fraction of its surface was imaged in high resolution, leaving vast areas unmapped. Future missions to Uranus could focus on Ariel, with detailed mapping that could uncover whether the canyons form a larger tectonic network or remain isolated. Evidence suggests that Ariel's orbit and axial tilt may have shifted over time, possibly triggering internal heating and causing cryovolcanic or tectonic processes. Understanding the history of Ariel's internal activity could provide valuable insights into the thermal evolution of Uranus's moons. Though Ariel shows no active plumes today, the relative youth of its surface suggests that it may still harbor internal heat, which could make it an interesting target for future exploration. Ariel may be a transitional world. Its most active phase may be over, but its frozen crust still holds clues to its dynamic past. Each fracture on Ariel's surface tells a story of internal forces that shape the moon, making it a fascinating object of study in the outer solar system. Ganymede, the largest moon of Jupiter, harbors a fascinating and complex magnetic field. This magnetic field is generated by a liquid metallic core, much like Earth's dynamo. However, what makes Ganymede stand out is its misaligned magnetic field. Unlike most planets, where the magnetic field is centered and aligned with the rotation axis, Ganymede's field is tilted both laterally and vertically. This misalignment creates unique interactions between Ganymede's magnetic field and Jupiter's massive magnetosphere, resulting in a dynamic and complex magnetic environment. The Galileo spacecraft first confirmed Ganymede's magnetic field in the 1990s. Unlike planetary magnetic fields, which are typically aligned with their rotation axis, Ganymede's field shifts as the moon spins. This creates a wandering magnetic pole that's not evenly distributed across the surface. As a result, different regions of Ganymede experience varying levels of space weather, especially near the magnetic poles and equator. These variations impact the surface, causing visible changes in color and even the degradation of surface ice. Ganymede's magnetic field also creates its own miniature magnetosphere within Jupiter's much larger one. This inner magnetosphere partially shields certain regions of the moon's surface from Jupiter's intense radiation, forming zones with vastly different exposure levels. These boundaries between different radiation zones shift constantly as both Ganymede and Jupiter move in their orbits. The auroras on Ganymede are another product of this unique magnetic interaction. Observations from ultraviolet light have shown that these auroras don't stay fixed near the poles, but instead move back and forth across the surface. This motion is driven by the interplay between Ganymede's internal magnetic field and the enormous magnetic forces exerted by Jupiter. Recent data from the Juno mission has provided more in-depth measurements of Ganymede's magnetic field, revealing that it's not only misaligned, but also structured with areas of localized intensification. This complexity hints at an active inner core still driving the magnetic dynamo beneath the surface. One particularly intriguing aspect of Ganymede's magnetic field is its potential interaction with the moon's subsurface layers. Magnetometer data suggests that there might be a salty ocean beneath Ganymede's icy crust, and as the moon rotates, this ocean slightly alters the magnetic field. This indirect evidence points to a conductive liquid layer buried beneath Ganymede's surface, which could offer more insights into its internal composition. Ganymede's misaligned magnetic field could also play a role in shaping its tectonic features. The moon's surface is filled with grooves, ridges, and fractures, some of which seem to align with areas of higher magnetic activity. This connection raises the question of whether electromagnetic forces are influencing the surface. In addition to tidal and thermal stresses, the unpredictable shifts in Ganymede's magnetic environment could pose challenges for future spacecraft missions. As spacecraft approach the moon, they must account for the rapid changes in the magnetic field, which could interfere with instruments and navigation. This is particularly important for missions like ESA's JUICE mission, set to orbit Ganymede in the 2030s. Ganymede's magnetic field is a significant puzzle for scientists and challenges our understanding of the minimum size and composition needed for a moon to generate a magnetic dynamo. Despite its unusual configuration, Ganymede shows that even moons can host complex magnetic environments beneath their frozen surfaces. Its tilted magnetic field is a constant reminder of the hidden complexities of small celestial bodies. Turning to Pluto, we find another fascinating feature: Sputnik Planitia. This massive icy basin forms the left lobe of Pluto's heart shape, and at first glance it seems like a smooth, bright plain covered in nitrogen ice. But beneath this serene exterior, Sputnik Planitia is an active and evolving region, driven by unusual thermal behavior. Evidence suggests that this basin is far from just a frozen feature. It pulses with rhythmic motion, tied to the internal heat of Pluto. The surface of Sputnik Planitia is segmented into polygonal cells, each spanning tens of kilometers. These shapes aren't random. They reflect convection processes occurring beneath the ice. Warm nitrogen from Pluto's interior rises to the surface, cools, and sinks again, causing the surface to slowly churn. This convection process renews the ice, smoothing out craters and keeping the surface looking youthful. Thermal models suggest that the floor of Sputnik Planitia is heated by residual radioactive decay from Pluto's rocky core. This heat is enough to soften and mobilize the nitrogen ice, allowing it to behave like a slow-moving fluid over long periods. Sputnik Planitia is located at a gravitational low point on Pluto, likely formed by a massive impact that created a basin, later filled with volatile ices. Over time, these ices have accumulated, and their redistribution has likely altered Pluto's orientation. This phenomenon, called true polar wander, may have caused shifts in Pluto's axial tilt, further influencing the behavior of Sputnik Planitia. The combination of its low elevation and high concentration of ice makes Sputnik Planitia act as a thermal sink. It gathers heat not only from Pluto's interior, but also from the atmosphere. During seasonal changes, nitrogen ice evaporates from other areas on Pluto and recondenses here, reinforcing the mass of the basin. This thermal cycle amplifies the contrast between Sputnik Planitia and the surrounding terrain, contributing to its dynamic behavior. The constant churning of the ice erases older craters, making this region one of the youngest-looking areas on Pluto, despite its ancient origins. Some of the basin's edges show evidence of glacial flow, where nitrogen ice slowly creeps downhill into adjacent valleys, redistributing mass and reflecting seasonal climate changes. The presence of pits and troughs across the surface may be the result of sublimation or thermal expansion. Infrared spectroscopy has revealed localized hotspots and compositional gradients within Sputnik Planitia, suggesting that different parts of the basin experience varying levels of heat retention and surface renewal. This variability is likely linked to the uneven distribution of heat beneath the surface, which is tied to the basin's depth and composition. The continuous movement of the ice creates a kind of thermal heartbeat, visible in both surface patterns and topographical changes. While these movements are imperceptible in real time, long-term data sets provide evidence of this slow but ongoing process. Future missions could further verify these movements with high-resolution imaging and thermal monitoring, allowing scientists to deepen their understanding of Pluto's hidden dynamics. Sputnik Planitia is now central to our understanding of Pluto, revealing that this distant world is far from a static, frozen rock. Instead, it is a geologically complex body with active features beneath its icy surface. The rhythmic motion of Sputnik Planitia, breathing in time with Pluto's hidden interior, adds another layer to our understanding of this enigmatic dwarf planet. Now let's move on to Ceres, the largest object in the asteroid belt. Despite its dry and cratered surface, Ceres harbors a surprising feature, a subsurface ocean. This hidden ocean challenges long-standing assumptions about the thermal and geological limits of small solar system bodies. Evidence of this ocean first emerged from data gathered by NASA's Dawn spacecraft. Gravity measurements revealed inconsistencies in mass distribution across the surface of Ceres, suggesting low-density material, possibly water or salt, beneath certain regions. One of the most striking features on Ceres is Okater crater, which displays signs of recent activity. Bright spots composed of sodium carbonate and other salts are scattered across the crater's surface. These bright patches are thought to have formed when salty brine seeped up through fractures in the crust, evaporated, and crystallized. This indicates that liquid water, or brine, exists beneath the surface, likely in a partially melted state. The heat required to maintain this liquid is thought to come from radioactive decay and the high concentration of salt, which lowers the freezing point of water. The bright spots near impact zones suggest that collisions may have triggered the upward flow of brine. Further evidence of this subsurface liquid comes from infrared and neutron spectrometry data collected by Dawn, which detected hydrated minerals and ammonia-rich compounds across Ceres's surface. These materials are consistent with aqueous alteration and cryovolcanic resurfacing, both of which require the presence of liquid water. The chemistry behind Ceres suggests that it has experienced a long-term interaction between rock and water. Seismic models based on its internal structure indicate that Ceres has a layered composition, a rocky core, a layer of muddy brine, and an outer crust made up of ice and hydrated minerals. The Moon's ocean is likely not global, but rather exists as pockets or layers of brine trapped between fractures in the crust. Even so, these partial liquid reservoirs make Ceres one of the most water-rich objects in the inner solar system. The icy outer crust of Ceres acts like an insulating shell, helping to preserve the liquid water beneath it over long periods. Some areas on Ceres, especially near the poles, appear to be thermally stable, making them potential hotspots where liquid could remain for geological periods. The crust itself is softer than expected, showing signs of gradual relaxation, a clear indicator of internal heat. While moons like Europa or Enceladus show large-scale surface deformations or active plumes, Ceres doesn't. Instead, it has subtle geological features like domes, fractures, and soft-edge craters that point to a past shaped by internal mobility. These features give us indirect but strong evidence for cryovolcanism, ice-driven volcanic activity, and the migration of fluids beneath the surface. Ceres' weak gravity and lack of an atmosphere make it an ideal location for studying how small bodies retain heat and water. The slow seepage of brine to the surface, leaving salt behind, mirrors processes seen in Earth's extreme cold deserts. These parallels help scientists understand how water behaves in environments that are marginal for life. While NASA's Dawn mission concluded in 2018, the data it returned continues to reshape our understanding of planetary evolution in the asteroid belt. The discovery of a potential liquid ocean beneath Ceres's icy crust places it among the most intriguing worlds for astrobiology. Future missions could use radar or landers to investigate Ceres's crust and its fluid reservoirs more directly. Now let's look at Mac, one of the largest known dwarf planets in the Kuiper belt. This frozen world, composed mainly of methane ice, has long been considered airless, its surface exposed directly to the vacuum of space. However, recent studies have revealed something unexpected, a transient, ultra-thin atmosphere that flickers in and out of existence, depending on Mac's position in its orbit. This ghostly atmosphere is not constant, but appears and disappears with the seasons. It's a delicate phenomenon driven by Mac's elliptical orbit around the Sun. In 2011, astronomers noticed that when Mech passed in front of a distant star, the starlight dimmed evenly and sharply, suggesting a solid body. However, closer inspection of the light curve showed faint diffraction effects, hinting at a very tenuous gas layer around the dwarf planet. Unlike Pluto's thicker, more stable haze, Mech's atmosphere would be nearly imperceptible, possibly measured in microbars. This atmospheric flicker is likely a result of Mech's orbit. As it nears the Sun during perihelion, the heat causes surface ices, mainly methane and nitrogen, to sublimate into gas. But as Mech moves farther from the Sun during aphelion, these gases refreeze and collapse back onto the surface, creating a temporary atmosphere that behaves more like a vapor cloud than a stable shell. Mech's surface contains frozen methane, ethane, and traces of nitrogen compounds known to sublimate at low temperatures. The delicate balance between solid and gas is crucial for the formation of Mech's atmosphere. Even a small temperature change can trigger localized outgassing events. Infrared data from telescopes have shown that the surface reflectivity changes over time, suggesting that the atmospheric cycles redistribute frost across the surface. Some areas darken and redden, while others brighten, evidence of chemical changes driven by varying pressure conditions. These surface changes may reflect where the atmosphere forms most readily. Unlike Pluto, MACD doesn't have active geology to sustain long-term atmospheric production. Its small size and low gravity make it harder to retain gas, yet the ephemeral atmosphere suggests a planet more dynamic than once believed. This opens up possibilities for periodic weather patterns, even in the outer reaches of the solar system. Future observations during occultation events will be crucial for understanding this atmospheric behavior. By monitoring changes in brightness, thermal emissions, and spectral features, scientists will be able to track how Mac's atmosphere cycles with its orbit. Additionally, Mac's moon, Mech2, might play a role in this behavior. While Mk2 is too small to directly affect the atmosphere, it could help stabilize the rotational dynamics of Mach, influencing its surface heating. This remains speculative since Mk2 has not yet been studied in detail, but it's a possibility worth exploring. Even at such a distance, Mach's subtle behavior challenges the idea of Kuiper belt objects being inert. Instead, it joins a growing list of outer solar system bodies with hidden complexities, where volatile chemistry and thermal cycles are still in motion. Its ghost atmosphere may not last forever, but it leaves traces that hint at the underlying dynamic processes happening on this faraway world. Moving on to Ceres once again, we encounter one of the most iconic discoveries from NASA's Dawn mission, the bright spots scattered across the surface of Ocata crater. These features, known as facula, shine with startling intensity against the otherwise dark terrain of Ceres. From orbit, they look almost artificial, like tiny lighthouses reflecting sunlight in sharp contrast to their surroundings. Their unexpected brightness and peculiar location immediately raised questions about their origin and composition. The largest of these bright spots lies within a depression called Cereolia Facula, at the center of Ocata crater. Surrounding it are smaller spots known collectively as venolia, which dot the floor like scattered jewels. Spectral analysis revealed that these spots are primarily composed of sodium carbonate, an alkaline salt that forms in highly concentrated water. This composition suggests that the bright material originated from briny liquid rising from beneath Ceres' surface. After an impact created Ocata crater, fractures in the crust allowed subsurface brine to ascend, leaving salts behind as the water sublimated into space. Over time, repeated upwelling and evaporation may have built up these concentrated reflective patches. The material is geologically young, estimated to be just a few million years old, which implies that Ceres has remained thermally active long after its formation. This recent activity defies expectations for a body of Ceres' size and location, making it one of the most intriguing small bodies in the inner solar system. High-resolution imaging from the Dawn spacecraft showed that some of the bright spots have flow-like textures, indicating that the material may have spread across the crater floor as it cooled and crystallized. These textures suggest cryovolcanic processes that are still active on Ceres, providing direct evidence of internal activity beneath its icy crust. The central spot's reflectivity is so high that sunlight can briefly overwhelm imaging sensors, highlighting how out of place it is on Ceres' otherwise dark surface. This stark contrast has made the bright spots a focal point for both scientific study and public fascination. The distribution of these spots across the crater is not uniform. Some are clustered along fractures, while others appear near collapsed regions and pit chains. This pattern suggests that subsurface channels once allowed brine to escape, and that impacts may have played a role in triggering geological resurfacing on icy bodies. Thermal models indicate that the energy required to support this activity likely comes from the decay of radioactive elements in Ceres' core. Combined with salt-laden water, this internal heat would be enough to keep brines mobile in localized pockets beneath the surface. The bright spots are not just remnants of past activity, they mark where fluid movements may still be occurring, albeit at a subtle pace. Even today, traces of water vapor have been detected near the bright spots, though the exact source remains uncertain. It's possible that sublimation continues under certain conditions, slowly releasing gas from beneath the crust. These bright spots, while visually striking, are more than just curiosities. They are chemical signatures of past mobility and resurfacing, giving us a glimpse into Ceres' ongoing evolution. Miranda, one of Uranus's moons, appears as though it has been violently torn apart and then reassembled, leaving behind scars that stretch for hundreds of kilometers. The moon's surface is dominated by formations known as coronae, large oval-shaped regions encircled by ridges and trenches. These structures rise dramatically from the surrounding plains, giving Miranda a lopsided terrace-like appearance. One of the most prominent, Arden Corona, features towering cliffs and fault lines that suggest massive tectonic uplift and crustal shifting. Miranda is home to some of the tallest cliffs in the solar system. Verona Rupes, for example, is a sheer cliff estimated to be 20 kilometers high, nearly 10 times the height of the Grand Canyon. The origin of this formation remains uncertain. It could be the result of global stretching forces, where the crust cracked, causing some parts to drop or rise due to internal stresses. Miranda's jumbled surface hints at a complex geological history. Some scientists believe that the moon may have undergone partial melting in the past, with warmer material rising and breaking through the crust. Others suggest that external impacts shattered the surface, which later refroze into a chaotic mosaic of terrain. Cryovolcanism, volcanic activity driven by ice rather than molten rock, has also been proposed as a contributing factor. If Miranda once had internal heat, possibly generated by tidal interactions with Uranus or neighboring moons, this could have mobilized icy material to the surface. This theory fits with the relatively young appearance of some regions, which lack the dense cratering typically seen in older terrain. The stark contrast between smooth plains and deeply fractured regions indicates that Miranda's surface has undergone resurfacing multiple times throughout its history. The moon likely went through cycles of heating and cooling, each time reshaping the crust in different ways. This episodic geology is rare for such a small moon, suggesting a surprisingly dynamic past. The dramatic topography on Miranda is also notable. Its plateaus rise steeply and drop sharply into rift valleys, while scarps and ridges intersect in intricate patterns. These sudden sharp transitions are unlike the more gradual features seen on larger moons, suggesting rapid and possibly violent geological changes. Much of Miranda remains unmapped. Voyager 2, during its flyby in 1986, imaged only one hemisphere, leaving the other half of the moon unexplored. What lies beyond the Terminator could be just as complex or even more bizarre than what we've already seen. Future missions to Uranus will likely target Miranda as a prime candidate for closer study. Despite its fractured surface, Miranda remains intact as a single body. The forces that tore it apart didn't succeed in completely breaking it, indicating a strong internal cohesion, perhaps due to a partially differentiated structure. Understanding why Miranda didn't completely break apart could reveal how small moons handle internal stress and retain their structural integrity. Miranda's chaotic surface offers a rare glimpse into tectonics on a small scale. Its plateaus and rifts are the frozen records of a moon that was once geologically alive, shaped by forces we still don't fully understand. Each feature tells a story of a dynamic past, preserved in ice and shadow on the edge of the Uranian system. Now let's move to Io, Jupiter's innermost large moon, which is the most volcanically active body in the solar system. Io's surface is constantly reshaped by volcanic eruptions, with over 400 volcanoes scattered across its landscape. These eruptions don't occur intermittently like Earth's volcanoes. Instead, they are ceaseless, reshaping Io's surface on a daily basis. Beneath a thin, fragile crust of sulfurous rock and silicate lava, Io is essentially a molten world. The intense volcanic activity is driven by tidal heating caused by Jupiter's immense gravitational pull. Io's elliptical orbit forces its interior to flex repeatedly, generating frictional heat that melts the internal layers, which is then released through continuous volcanic eruptions, creating rivers and lakes of molten rock. This relentless volcanic activity prevents Io from forming a stable, long-lasting crust. The volcanic plumes erupting from Io's surface are breathtaking, some reaching over 300 kilometers into space, These plumes consist mostly of sulfur dioxide, along with sulfur particles and silicate dust. When these materials fall back to Io's surface, they coat it with bright deposits of vivid yellow, orange, and red, creating patterns that are constantly changing. As a result, Io's surface is in a perpetual state of renewal, with layers of freshly deposited volcanic ash and sulfur compounds accumulating constantly. High-resolution images from the Galileo spacecraft and more recent Juno flybys show dramatic changes in Io's surface over just a few months. Entire volcanic regions vanish, lava flows shift, and new calderas open, demonstrating that Io's surface is among the youngest and most dynamic in the solar system. This rapid resurfacing means that craters rarely survive for long. They are almost immediately erased by volcanic activity. One of I's largest volcanoes, Loki Patera, is a massive lava lake nearly 200 kilometers wide. Observations show that Loki periodically undergoes massive overturns, resurfacing itself like a boiling cauldron. This suggests that there's a persistent convecting magma reservoir beneath the surface, constantly feeding the volcanic cycle. This ongoing internal magma circulation maintains I's high heat flow, ensuring that volcanic activity continues unabated. Unlike other moons, Io lacks substantial amounts of water or ice. Its surface and interior are predominantly rocky and sulfurous. The intense volcanic activity releases gases that form a thin atmosphere around Io, primarily consisting of sulfur dioxide. This atmosphere is tenuous and fluctuates in density depending on volcanic output and solar radiation. The variability in Io's atmosphere provides valuable insights into how volcanism affects environmental conditions on moons and planets. Io's volcanic plumes also interact with Jupiter's magnetosphere, feeding charged particles into space around the planet. This interaction creates a vast plasma torus, a donut-shaped ring of energetic ions trapped in Jupiter's magnetic field lines. The plasma torus not only affects Jupiter's eruptors, but also generates intense radiation belts around the planet. In this way, Io's volcanic activity doesn't just shape its own surface, it also influences the broader Jovian environment. The volcanic activity on Io is not uniform. Some regions experience gentle, constant lava flows, while others undergo explosive eruptions that dramatically reshape the terrain. This variability helps scientists study a range of volcanic processes within a single body, offering a unique laboratory for planetary geology. Monitoring Io's surface and subsurface activity will help improve models of volcanic behavior, which can be applied to other planetary bodies throughout the solar system and beyond. Future missions to Io will provide new insights into tidal heating, volcanic cycles, and the forces that shape planetary geology on a global scale. Understanding Io's extreme volcanism is key to grasping how both internal and external forces shape the evolution of planetary bodies. In many ways, Io is the purest example of volcanism at work, a world that is constantly on the brink of eruption, molten and ever-changing. Lastly, let's look at Pluto, which long ago was thought to be a lifeless ice ball at the edge of the solar system. But the New Horizons spacecraft revealed an entirely different story, one filled with stunning landscapes shaped by frozen nitrogen. Within Sputnik Planitia, the distinctive heart-shaped plain of Pluto, winding networks of valleys and channels, remarkably similar to Earth's rivers, were discovered. These channels, however, are not formed by water, but by flowing nitrogen ice. At Pluto's extremely low temperatures, around -230 degrees Celsius, nitrogen behaves like glaciers on Earth, slowly moving downhill due to gravity and thermal gradients. Over time, these nitrogen glaciers carve intricate channels, creating features that resemble terrestrial river systems. New Horizons captured detailed images of these nitrogen flows, showing smooth, sinuous channels winding through rugged mountainous terrain. The flows originate from higher elevations and gradually descend toward lower plains. The gentle slopes allow the nitrogen ice to move at a pace measured in centimeters per year, a slow process by Earth's standards. Despite this, the continuous movement gradually erodes valleys and redistributes surface material. The intricate network of nitrogen rivers seen in Sputnik Planitia suggests an ongoing geological cycle, Surface nitrogen sublimates into Pluto's thin atmosphere under sunlight, then refreezes in colder, shaded regions. This cycle of deposition and erosion continuously shapes Pluto's surface features, ensuring that the landscape remains dynamic over millions of years. Unlike Earth's rivers, which are driven by rainfall and melting water, Pluto's nitrogen rivers are primarily driven by internal heat from radioactive decay, tidal interactions with its moon Saturn, and seasonal changes in solar radiation. These conditions warm the subsurface nitrogen, allowing it to flow. The branching patterns of these nitrogen rivers also resemble terrestrial river deltas, indicating that nitrogen ice may periodically melt or soften enough to behave fluidly, forming smaller streams. These branching formations may be a sign of warmer conditions in Pluto's geological past, potentially linked to changes in its orbital or axial tilt. Studying these features gives scientists valuable insights into Pluto's climate history. Pluto's surface showcases dynamic changes through active resurfacing processes, where older terrain is consistently buried beneath fresh layers of nitrogen ice. This phenomenon plays a crucial role in understanding Pluto's surprisingly youthful geological features. The dwarf planet's nitrogen rivers not only reshape the surface but also impact its atmospheric composition. Each season, the sublimation of nitrogen ice adds gases to the atmosphere, sustaining Pluto's faint hazy layers. These atmospheric movements, in turn, influence the distribution and flow of surface nitrogen ice, creating a tightly interconnected system between the surface and atmosphere that continuously shapes Pluto's evolution. Looking ahead, further exploration of Pluto could offer more precise data on how nitrogen ice behaves under extreme environmental conditions. Future missions, whether orbiting or landing on Pluto, could measure the flow rates, temperatures, and chemical makeup of nitrogen, giving us deeper insights into these frozen rivers and their geological implications. Such missions could potentially revolutionize our understanding of geological activity on small, distant worlds, providing clarity on how planetary systems evolve far from the Sun. Moving to Europa, one of Jupiter's major icy moons, we encounter an invisible yet profoundly influential phenomenon: a cloud of electrically charged particles. This charged particle environment arises from interactions between Jupiter's intense magnetic field and Europa's icy surface. Radiation from Jupiter bombards Europa, ejecting water molecules into space, which then form a tenuous cloud of plasma and ions that encircle the Moon. The cloud primarily consists of oxygen and hydrogen ions, the byproducts of water-ice dissociation caused by high-energy radiation. Although Europa lacks a thick traditional atmosphere, this invisible cloud acts like a protective shield, engaging dynamically with Jupiter's magnetosphere. This type of phenomenon is known as an induced magnetosphere, where the magnetic environment is generated not by the Moon's own magnetic field, but through interactions with Jupiter's field. The Galileo spacecraft first observed this charged environment in the 1990s, revealing that Europa causes disturbances in Jupiter's magnetic field. These disturbances occur when Jupiter's rotating magnetosphere sweeps by Europa, energizing particles from the Moon's surface and creating this localized plasma cloud. These interactions also produce faint auroral emissions that can only be seen in ultraviolet light, underscoring Europa's magnetic impact. The size of Europa's charged particle cloud changes depending on its orbital position, expanding or contracting as the Moon moves closer to or farther from Jupiter. During certain phases of its orbit, the cloud intensifies, influenced by stronger interactions with Jupiter's magnetospheric plasma. These effects could have an impact on Europa's surface chemistry, potentially affecting the composition of its subsurface ocean as well. Charged particles interact with Europa's surface ice, chemically altering it and creating complex molecules that could play a significant role in astrobiological studies. Europa's subsurface ocean, located beneath several kilometers of ice, is electrically conductive due to the presence of dissolved salts. This ocean acts as a conductor within Jupiter's magnetic field, amplifying Europa's magnetic response and contributing to the stability of the charged particle cloud. Measuring this cloud could, therefore, give us indirect insights into the ocean's depth and salinity. The presence of this charged environment presents both challenges and opportunities for future missions. Spacecraft seeking to study Europa must navigate through intense radiation fields, requiring advanced shielding and meticulous planning. However, this particle cloud provides an incredible opportunity for researchers. By studying the composition and behavior of these particles, scientists can infer the characteristics of Europa's ocean without the need to penetrate its thick ice shell. Moreover, the charged cloud interacts with Jupiter's larger magnetosphere, adding particles that contribute to the planet's magnetic field. This interaction offers a valuable opportunity to better understand the broader processes at work in Jupiter's system and beyond. Europa thus serves as a natural laboratory for plasma physics, and future missions like NASA's Europa Clipper and ESA's JUICE will gather data to refine our models of Europa's hidden environment. These spacecraft will analyze magnetic fluctuations, particle composition, and plasma densities, providing crucial insights into the Moon's interior and the potential for life. Shifting focus to Titan, Saturn's largest moon, we encounter a world shaped not by water but by liquid methane and ethane. Titan's nitrogen-rich atmosphere allows methane to exist in liquid form, flowing in vast rivers that carve intricate channels across the icy surface. These methane rivers form complex patterns, resembling terrestrial river systems with tributaries, deltas, and even occasional waterfalls. Observations by the Cassini spacecraft revealed Titan's river networks in great detail. Radar imaging allowed scientists to peer through Titan's thick atmosphere, revealing channels hundreds of kilometers long, winding through valleys and plains. These rivers eventually feed into large methane lakes and seas located near Titan's poles. This methane river system continuously reshapes Titan's surface, transporting sediment and eroding terrain in a manner strikingly similar to Earth's water-based processes. Titan's rivers also feature turbulent zones, where methane currents swirl into vortex-like patterns. These formations occur when fast-moving methane encounters areas with differing surface elevations or sediment buildups, creating localized turbulence. The dynamics of these methane rivers closely mirror those of Earth's water systems, highlighting the universality of certain fluid behaviors across diverse environments. Understanding these fluid dynamics on Titan can deepen our understanding of how fluids behave in other planetary settings. A prominent example of Titan's river systems is the Vid Flumina, which drains into Titan's largest methane lake, Ligaea Mare. Vid Flumina showcases branching patterns and extensive deltas, indicating that liquid methane has been flowing through this region for an extended period, depositing sediment and reshaping the landscape. Like Earth's monsoon cycles, Titan experiences seasonal changes, with methane rainfall swelling its rivers during stormy seasons. However, the fluid in Titan's rivers behaves quite differently from water due to methane's lower density and viscosity. This results in slower erosion and sediment transport, meaning Titan's landscapes evolve at a gentler pace than Earth's dynamic geology. Over millions of years, though, Titan's methane rivers could significantly alter its topography, creating valleys, plains, and shorelines. Titan's methane rivers offer fascinating insights into its past climatic conditions. Geological evidence suggests that Titan has experienced periods of higher methane rainfall, possibly linked to changes in its orbit or atmosphere. By studying river patterns and sediment deposits, scientists can reconstruct Titan's historical climate, uncovering cycles of warming and cooling that have shaped its surface over time. This process is similar to how geologists on Earth study past climates through sediment analysis. In the near future, NASA's Dragonfly drone mission will directly explore Titan's surface and rivers. Dragonfly aims to collect sediment samples from the riverbeds, analyze the composition of methane, and observe fluid dynamics up close. This direct exploration will provide invaluable data about Titan's geological processes and the chemical interactions occurring in its rivers and lakes. These findings could also provide clues about prebiotic chemistry, as organic molecules transported by Titan's rivers could accumulate in environments conducive to life. Mars, unlike most planets, hides a faint yet fascinating feature, a dust ring that was once only theorized but has now been confirmed by simulations, indirect measurements, and infrared observations. While its density is far lower than Saturn's iconic rings, being thousands of times thinner, This dust ring persists due to the continuous replenishment from Phobos. The Moon's orbit is slightly tilted and asymmetric, resulting from the complex gravitational interactions between Mars, Phobos, and the Sun. Rather than being made of ice like Saturn's rings, Mars's dust ring consists mostly of rocky dark particles. The visibility of these particles depends on how sunlight scatters off them, making the ring extremely difficult to capture in direct images. Most spacecraft passing through Mars's orbit sail through it without encountering any noticeable resistance, since the dust is so sparsely distributed. This makes the dust ring more of an intriguing scientific curiosity than a spectacular visual phenomenon. Although challenging to observe, studying this faint feature can reveal a great deal about the gradual erosion of Phobos over millions of years. As the Moon slowly wears away, its mass and surface characteristics are altered. The dust ring, therefore, is not just a passive presence. It signifies slow but ongoing geological changes. It also raises important questions about the future of Phobos, which is slowly spiraling inward toward Mars. This decay in Phobos' orbit may eventually cause it to get so close to Mars that it could disintegrate, forming a much more prominent ring of debris. The current dust ring might be seen as a precursor to this dramatic transformation. Although this event is far off, it underscores why studying even minor features like this dust ring is crucial. Data collected from orbiters such as Mars Express and MAVEN are helping scientists refine models about the dust ring's behavior. By observing the way the particles are distributed and how they gradually fade away, researchers can test theories on planetary ring formation and stability. This knowledge extends beyond just Mars. It can also provide insights into other ring-bearing bodies across the universe, including exoplanets. The discovery of Mars's dust ring reminds us that even planetary systems without dramatic features like Saturn's rings can still harbor subtle hidden phenomena. Mars, once thought to lack any kind of ring system, has its own hidden ring, a feature that challenges our previous understanding and encourages us to rethink the very definition of planetary rings. It highlights how even the tiniest particles slowly drifting through space can hint at the geological processes shaping a planet's future. Now let's turn to Saturn's North Pole, where we find one of the most astonishing features in our solar system, a massive hexagonal jet stream encircling the planet's pole. This geometric wonder is unlike any other storm seen elsewhere. It stretches around 30,000 kilometers in diameter, more than twice the width of Earth, and remains strikingly stable. Discovered during the Voyager missions in the 1980s and later closely imaged by Cassini, Saturn's hexagon is formed by winds traveling at over 300 kilometers per hour, tracing out sharp corners as they shift direction. At the center of this hexagonal shape sits a massive polar vortex, a swirling storm with a well-defined center, much like a hurricane. The origin of the hexagon lies in fluid dynamics. Laboratory experiments on spinning fluid show that polygonal shapes like hexagons can form when different layers of fluid move at different speeds. The unique atmospheric conditions in Saturn's atmosphere likely create such effects, resulting in a stable standing wave pattern that maintains the hexagonal shape. The phenomenon serves as a giant, natural experiment in planetary fluid mechanics. What makes this hexagon even more remarkable is its longevity. Observed over several decades and across Saturn's seasons, the hexagon has maintained a consistent size and shape, unlike the unpredictable and shifting weather patterns seen on most other planets. This stability suggests a unique equilibrium in Saturn's atmosphere that has persisted for an exceptionally long time. The colors within the hexagon also change with the seasons. In Saturn's winter, the structure appears mostly grey and uniform, but as spring approaches in the northern hemisphere, the hexagon transforms, taking on golden hues. This color shift is caused by photochemical reactions in the upper atmosphere, triggered by solar radiation. These changes reveal more than just a storm's movement. They hint at ongoing chemical processes within Saturn's atmosphere. The hexagon also rotates in sync with Saturn's deeper atmosphere, which means it stays locked in place rather than drifting like surface storms. This connection between the upper and deeper layers of the atmosphere gives scientists a rare chance to study Saturn's internal atmospheric dynamics. The exact depth of the storm remains a mystery, but models suggest that the vortex may extend hundreds of kilometers below Saturn's cloud tops. Cassini's close passes have allowed scientists to detect smaller vortices and wave patterns at the edges of the hexagon, indicating complex interactions in the atmosphere. These ripples provide crucial clues to the forces at play, such as rotation, pressure differences, and temperature changes, that help maintain the hexagon's structure. The fact that Saturn has no corresponding hexagon at its south pole raises intriguing questions about atmospheric symmetry and how solar heating influences atmospheric circulation. Why does the hexagon form at one pole but not the other? This remains an atmospheric enigma, deepening our understanding of planetary weather patterns. Saturn's hexagonal storm is an awe-inspiring example of how nature can produce perfect geometry on a planetary scale, using only wind and temperature. It challenges our previous notions of weather systems and stands as one of the solar system's most elegant and mysterious features. Next, we turn to Saturn's E-ring, which is unlike any of the planet's other rings. The E-ring's composition and behavior defy our expectations. Unlike the dense icy B and C rings, the E-ring is faint and diffuse, extending from the orbit of Mimas all the way out to Titan. The source of this unusual ring is the icy moon Enceladus, whose south pole ejects plumes of water vapor and ice at high speeds. These particles escape the moon's gravity and enter orbit around Saturn, contributing to the hazy ring. The dynamics of these particles are influenced not only by gravity, but also by Saturn's magnetic field, solar radiation, and plasma interactions. The particles, often no larger than a micron, are easily disturbed by electromagnetic forces. Some spiral inward towards Saturn, others move outward, while some adopt elliptical or inclined orbits within the E-ring. This chaotic movement gives the E-ring its ghostly, diffuse appearance. The Cassini spacecraft's instruments detected varying particle speeds and densities depending on their distance from Enceladus, revealing the moon's crucial role in maintaining the ring. Many of the particles in the E-ring travel at speeds greater than 400 meters per second, a result of the force behind Enceladus geysers, which are driven by internal tidal heating. The fact that such small particles can be expelled at these high speeds and still maintain coherent orbits suggests that the geysers are incredibly powerful and consistent, contributing to the stability of the E-ring over millions of years. The E-ring's optical properties change with the angle of sunlight and the composition of the particles. Observations in ultraviolet and infrared wavelengths reveal subtle variations in particle size and structure, with some even containing organic molecules or salts. This indicates a connection between the E-ring and the subsurface ocean on Enceladus. The particles in the E-ring are short-lived, gradually eroded by micrometeorite impacts and radiation, which means they must be continually replenished by Enceladus's geysers. Without this constant source, the E-ring would vanish within a few thousand years. This constant cycle of creation and destruction gives the E-ring an almost living quality. Studying these fast-moving particles helps scientists understand the processes shaping planetary rings and the moon's hidden ocean chemistry. The E-ring, though faint and ghostly in appearance, provides valuable insights into particle behavior in low-density environments. It acts as a natural laboratory for studying dust grain movement, magnetic field interactions, and collisional dynamics. Despite its elusive nature, the E-ring has a significant effect on the nearby moons of Saturn. Tiny ice particles in the ring continuously bombard these moons, changing their surfaces and potentially delivering chemical compounds that might be crucial for understanding the chemistry of the system. This exchange of materials between the E-ring and the moons creates a unique network of physical and chemical interactions within the Saturnian system. The E-ring connects multiple bodies, linking them into a shared web of material exchange. This makes the ring more than just a faint feature. It's a dynamic component of Saturn's larger ecosystem. The collisions between the particles and the moons are not just random impacts but crucial events that provide clues about the history and future evolution of Saturn's rings and moons. These interactions highlight how even the smallest features in space can have significant effects on nearby celestial bodies, contributing to the larger story of the solar system. Now let's turn our attention to Vesta, one of the largest objects in the asteroid belt, which bears evidence of some of the most violent collisions ever recorded in the solar system. Vesta isn't like most other asteroids. It's a differentiated body, meaning it has a distinct crust, mantle, and core, much like a small planet. This differentiation gives Vesta a unique history and allows scientists to study its internal processes and evolution. The scars of past collisions are visible across its surface, including deep basins and jagged ridges that tell the story of cataclysmic impacts that reshaped its structure. One of Vesta's most striking features is the Rhea Basin at its south pole, an impact structure spanning 500 kilometers across and plunging 20 kilometers deep. The forces required to create such a feature were immense, with the impact likely caused by a massive projectile slamming into Vesta at tens of thousands of kilometers per hour. The collision didn't just excavate surface material, it also shattered Vesta's interior layers, exposing ancient rocks that had been hidden for billions of years. The seismic waves from this impact spread throughout the asteroid, creating fractures, troughs, and ridges on the opposite side, creating a global pattern of grooves circling its equator. These geological features suggest that Vesta's crust was rigid enough to transmit large-scale stress from such an impact. The Rhea Silvia impact also ejected vast amounts of debris into space, some of which became V-type asteroids in the main asteroid belt, while smaller fragments eventually reached Earth as HED meteorites. This link between Vesta and meteorites found on Earth makes it one of the few bodies directly connected to our planet's geological history, intertwining its story with our own. The impacts that shaped Vesta also altered its overall shape, giving it a slightly flattened, irregular appearance. These collisions mixed crustal and mantle materials, exposing minerals that had been buried deep within. The Dawn spacecraft, which studied Vesta in detail, revealed olivine-rich regions that likely formed during these ancient impacts. By studying these minerals, scientists can learn more about Vesta's early differentiation and thermal evolution, helping them understand the processes that shaped the formation of planets. Despite the passage of billions of years, smaller collisions continue to shape Vesta's surface today. New craters overlap older basins, revealing a history of ongoing bombardment in the asteroid belt. These impacts may be less dramatic than the ancient ones, but they still contribute to the surface regolith and alter the brightness patterns visible from space. By studying the sequence of these craters, scientists can create a timeline of events on Vesta's surface that stretches back over 4 billion years. Vesta's ability to preserve the signatures of these impacts over such a long period makes it a geological time capsule, offering a glimpse into the violent environment of the early solar system. Vesta's surface features provide a detailed record of the early stages of planetary formation, offering valuable insights into how planets evolve and survive bombardments that would easily shatter smaller bodies. Its ancient impacts hold the key to understanding not just Vesta's history, but also the broader processes that shape the solar system. Turning to the Sun, we encounter one of the most powerful phenomena in our solar system: solar plasma cascades. These massive bursts of charged particles, known as coronal mass ejections (CMEs), are among the most energetic events in the solar system. They consist of protons, electrons, and magnetic fields that surge outward from the Sun at speeds of up to 3,000 kilometers per second. As they travel through the solar system, these plasma waves create vast spirals that can stretch across millions of kilometers. CMEs are not just local solar events. They have far-reaching effects, impacting the entire heliosphere and influencing the magnetic fields of planets, comets, and moons across the solar system. CMEs can cause geomagnetic storms on Earth, affecting everything from satellites to power grids to atmospheric chemistry. These bursts of solar material are powerful enough to disturb interplanetary space, compressing solar wind zones and accelerating particles. Spacecraft like SOHO and Stereo have captured high-resolution images of these massive eruptions, revealing complex layered structures shaped like loops or bubbles. Each CME is unique, with variations in intensity and shape depending on the location and conditions of its eruption on the Sun's surface. The effects of CMEs extend to every planet in the solar system. Mercury, with no significant atmosphere or magnetic field, experiences the full brunt of these plasma waves, which strip away its surface material. On Earth, the magnetic field offers some protection, but auroras and radio disturbances are common side effects. Even Jupiter and Saturn, with their massive magnetospheres, feel the effects of these solar eruptions, experiencing compression and realignment during intense CME events. As these plasma cascades travel outward, they lose energy but continue to interact with dust, comets, and the plasma environments of distant moons. At the orbit of Pluto, for example, even though the solar wind slows dramatically, sensitive instruments on deep space probes can still detect the effects of these massive plasma bursts. CMEs help shape the boundaries of the heliosphere, the Sun's protective bubble. When Voyager 1 crossed the edge of the heliosphere, it still detected fluctuations caused by distant solar eruptions, demonstrating the far-reaching influence of these plasma cascades. Studying these events helps scientists understand space weather and its impact on planetary habitability. For example, the loss of Mars's atmosphere is thought to have been exacerbated by solar wind stripping, a process that intensifies during large CME events. Understanding these interactions is critical for explaining atmospheric loss on other planets and designing future space missions, especially those traveling beyond Earth's magnetic protection. Solar plasma cascades are unpredictable and sometimes catastrophic, reminding us that even in the quiet expanse of space, immense forces can sweep through, reshaping everything in their path. Lastly, let's talk about Charon, Pluto's largest moon, which was once believed to be an airless, inert world. Recent data from NASA's New Horizons mission, however, has revealed hints of a tenuous atmosphere, so thin that it has been nicknamed a ghost atmosphere. Unlike Pluto's nitrogen-rich envelope, Charon's atmosphere appears to form intermittently, disappearing just as quickly as it appears. This fleeting atmosphere is thought to develop when sunlight hits Charon's cold surface, releasing gases like nitrogen and methane through sublimation. These particles linger briefly before escaping into space due to Charon's low gravity. The entire process may last only a few days or weeks, driven by solar cycles and temperature fluctuations. New Horizons ultraviolet imaging has shown signs of haze or scattering particles above Charon's surface, further supporting the existence of this transient atmosphere. While its pressure is minuscule, trillions of times lower than Earth's, this ephemeral atmosphere provides valuable clues about the Moon's surface and its interaction with solar radiation. It also raises new questions about the conditions that might allow such an atmosphere to form, survive for short periods, and then dissipate. The faint reddish stain known as Maunder-Macola on Pluto's surface is believed to be the result of methane compounds released from the planet's escaping atmosphere. These compounds are then altered by radiation from the Sun. While Charon, Pluto's largest moon, doesn't retain a permanent atmosphere due to its lack of a magnetic field and low gravity, it periodically outgasses materials which could contribute to or redistribute these polar compounds. Solar radiation and cosmic rays relentlessly erode any atmosphere that forms, making it impossible for Charon to keep volatile elements for long periods. Yet despite these challenges, the recurring appearance of trace gases on Charon suggests a cycle, a brief release of gases, a temporary suspension, and eventual dissipation. This pattern hints at more dynamic chemical activity on Charon than scientists once thought for distant icy moons. Understanding Charon's ephemeral atmosphere could also shed light on similar processes occurring on other objects in the Kuiper belt. Many of these icy bodies are thought to experience seasonal changes, shedding and reabsorbing volatile substances in response to the distant sunlight. Thus, Charon's atmosphere serves as a key example for studying transient atmospheres in extreme environments. One lingering question is whether Charon's atmosphere ever becomes substantial enough to affect surface temperatures or even cause erosion. Even a slight atmospheric pressure could influence the accumulation of frost or the movement of particles across the surface. Future missions will need to closely monitor the Moon over time to detect such subtle changes. If Karma's atmosphere is confirmed to fluctuate in such ways, it could represent a class of planetary environments where the boundary between surface and space becomes blurred, with particles drifting briefly above the crust. These ghost atmospheres challenge the traditional definitions of what constitutes a true atmosphere and expand our understanding of where atmospheric physics can be studied in slow motion. The flyby of New Horizons was too brief to capture the full cycle of atmospheric changes, but extended observations from orbit could determine whether Charon's atmosphere fluctuates seasonally or responds to local temperature changes. Until then, The moon remains shrouded in mystery, its once airless face possibly more dynamic than previously thought. Turning to Neptune, we encounter one of its most puzzling features, the migration of massive dark vortices. These gargantuan storms, often larger than Earth, emerge, drift, and vanish unpredictably. The most famous of these storms, the Great Dark Spot, was observed by Voyager 2 in 1989 in Neptune's southern hemisphere. When Hubble revisited the region years later, the storm had vanished, only for new dark spots to emerge in the northern hemisphere. This suggests that these vortices don't simply fade, they appear to move or reform in different latitudes, pointing to an underlying atmospheric mechanism that remains poorly understood. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's dark spots are transient and their movement is not linear. These spots are believed to be high-pressure systems, which are the opposite of typical planetary storms. Instead of spiraling inward like hurricanes, Neptune's vortices spin in the opposite direction, creating a downward flow at their centers. Surrounding them are bright clouds made of methane ice, which make the spots stand out in infrared and ultraviolet wavelengths. As these dark spots migrate, some shrink and disappear, while others break apart or merge with other vortices. The mechanics behind these changes remain largely theoretical, due to a lack of continuous high-resolution observations. These migrating storms offer valuable insights into Neptune's deeper atmosphere. Their existence suggests that there are stable structures deep beneath the clouds capable of anchoring such massive pressure systems. However, their disappearance also indicates a certain fragility, as if the balance sustaining them can collapse with the smallest shifts. This paradox, where the storms are both stable and fleeting, makes Neptune's atmosphere a subject of fascination. Unlike Earth or Jupiter, Neptune's atmosphere is dominated by supersonic winds and extreme cold, which significantly affect how these storms behave. Despite receiving very little solar energy, Neptune hosts some of the most powerful winds in the solar system, providing the conditions that foster the creation of these migrating vortices. The energy source for these storms remains unclear, though some scientists suggest that internal heat left over from Neptune's formation could be responsible. The planet radiates more energy than it receives from the Sun, fueling convection currents that may help form and maintain these massive storms. However, observing this internal dynamic directly, especially from Earth, remains challenging. Hubble is our primary tool for tracking these storms, but even its observations are brief snapshots. Future missions equipped with long-term monitoring instruments may provide more detailed information about the full life cycles of these dark spots. For now, each new appearance of these migrating storms remains a captivating mystery unfolding in slow motion. Next, we shift our focus to Saturn's iconic rings, which appear smooth and symmetrical from a distance, but reveal a dynamic, ever-changing landscape up close. This intricate ring system is sculpted by a collection of small moons that play crucial roles in shaping, maintaining, and even dividing the ring structures. Without these moons, Saturn's rings might dissolve into chaos. Prometheus, Pandora, Daphnis, and Pan are just a few of the famous shepherd moons that patrol the edges and within the rings. Each moon exerts its gravitational influence on the particles within the rings, ensuring that the structures remain intact and orderly. Prometheus and Pandora are particularly active, patrolling narrow gaps between the rings and using their gravity to tug on the strands, creating braided, kinked patterns. Daphnis orbits within the Keeler gap, raising ripples that stretch for hundreds of kilometers as it moves through. Pan, shaped like a flying saucer due to an equatorial ridge, orbits within the ring gap, pulling particles into delicate wave patterns that radiate outward. These waves are not random, they are governed by the gravitational forces exerted by the shepherd moons, and each moon leaves its own unique imprint on the ring structure. These intricate patterns of waves, gaps, and ringlets are constantly shifting as the moons interact with the particles in the ring. The role of the shepherd moons is vital in maintaining the stability of the rings. These moons corral the particles within the rings, preventing them from drifting into neighboring regions. When particles stray, the moon's gravitational pull gently redirects them, keeping the rings sharp and defined. However, not all interactions are gentle. Close approaches between moons and ring particles can create abrupt edges, vertical structures, and even eject material into new orbits. Some moons, such as Atlas, sweep up material along their path, adding to nearby ring arcs. These interactions make Saturn's rings one of the most dynamic regions in the solar system. The Cassini spacecraft's mission revealed countless details about these sculpting moons. It captured images of spiral density waves, gravitational wakes, and the delicate interplay between moons and particles at every scale. These observations confirmed that Saturn's rings are far from static. They are alive with motion, conflict, and subtle balance. By studying these shepherd moons, scientists also gain insights into planetary disk formation, as the processes seen around Saturn resemble those that govern the early formation of planets around young stars. Gaps, wakes, and embedded bodies are features shared between Saturn's rings and the protoplanetary disks that form around young stars, making Saturn a miniature version of cosmic evolution. These moons may be small, but their influence is vast. A shepherd moon just tens of kilometers wide can control ring structures that stretch across thousands of kilometers. This disproportionate effect highlights the power of gravitational mechanics, showing how even the smallest bodies can exert significant control over celestial structures. Finally, we turn our attention to Eris, a distant dwarf planet in the scattered disk beyond Pluto. Eris was once considered a rival to Pluto in terms of its size and mass, and its discovery in 2005 played a significant role in Pluto's reclassification as a dwarf planet. Eris is not alone, however. It has a moon named Dysnomia, and together they perform a unique gravitational dance in one of the solar system's most remote regions. Their orbital interaction provides rare insights into mass composition and dynamics far beyond the Kuiper belt. Dysnomia orbits Eris every 16 days in a nearly circular path about 37,000 kilometers away. Despite its distance from the Sun, Dysnomia's movement is surprisingly stable, suggesting that Eris has a strong gravitational influence. By measuring Dysnomia's orbit, astronomers were able to calculate Eris's mass, confirming it as one of the densest known dwarf planets. This gravitational interaction between Eris and Dysnomia reveals more than just orbital mechanics. It provides clues about the composition of both bodies. Eris's density suggests that it has a rocky interior covered by a thin layer of ice, distinguishing it from other icy objects like Pluto. Dysnomia, on the other hand, is likely darker and may be a captured body, or the result of a massive impact. The differences between Eris and its moon Dysnomia point to complex histories in the outer solar system. However, studying this system in detail proves difficult due to its isolation. Dysnomia, being faint, is often lost in the glare of AIS, and requires either space telescopes or advanced ground-based optics for resolution. Despite these challenges, the data we have collected so far has reshaped how we classify and understand trans-Neptunian objects. Eris and Dysnomia have become benchmarks in the study of dwarf planet systems. Similar to Earth and its moon, Eris and Dysnomia may be tidally locked, meaning that over time their spins could gradually slow and synchronize, leading to a balanced orbit. Tidal evolution like this is common in distant binary systems, showing that even in near-total darkness, these subtle interactions continue. AIS's tilt and slow movement across the sky make it tricky to track, as the orientation relative to Earth changes slowly. This variability impacts how we observe Dysnomia, sometimes giving us ideal edge-on views for calculating mass, while other times making detection difficult. Long-term monitoring is critical to refining models of their motion. Observing Eris reveals that it reflects more sunlight than expected, suggesting that its surface is covered with fresh, possibly renewed frost. Dysnomia, on the other hand, appears much darker, implying a more primitive surface or one less exposed to resurfacing processes. This stark contrast raises intriguing questions about the formation of these two bodies and whether Dysnomia was once part of Eris itself. Future missions to the outer solar system could include flybys or orbiters targeting Eris and Dysnomia, offering a chance to study their geology, internal structure and interactions, data that is impossible to gather from Earth. Until such missions occur, their synchronized movement remains one of the most distant gravitational harmonies we've detected. Moving on to Uranus, the planet is known for its extreme axial tilt, pale aquamarine color, and cold atmosphere. However, hidden within its orbital domain is a system of moons and rocky fragments that orbit in near silence. These are not the well-known moons like Titania or Oberon, but a collection of faint, irregular bodies and debris that are often hard to distinguish from background stars. Together, they form a ghostly presence around Uranus. These fragments are believed to have originated from ancient collisions or gravitational disruptions. Some may be remnants of shattered moons, while others could have been captured from the Kuiper belt long ago. Their orbits are often inclined and eccentric, suggesting a violent and chaotic history. Many of these objects remain unnamed or unconfirmed, and due to their small size and darkness, they are difficult to detect. Uranus is known to have at least 27 moons, though new candidates continue to be found in deep sky surveys. Many of these smaller moons are no more than a few kilometers across, and their dark surfaces are coated with carbon-rich material which absorbs more light than it reflects. As a result, they are nearly invisible to even advanced telescopes. These fragments are silent in every sense, producing no noticeable thermal emissions, radio signals, or detectable outgassing. They drift in cold darkness, primarily affected by gravity and occasional impacts. However, their slow movement through Uranus's gravitational influence helps maintain the planet's complex system of faint rings and dusty arcs. Some of these bodies pass dangerously close to Uranus's outer rings, subtly influencing their structure. Minor gravitational tugs from these small moons might explain certain asymmetries or gaps within the rings, offering a glimpse into an invisible choreography that affects the planet's ring system. Even a moon just tens of kilometers wide can leave a gravitational imprint that shapes the rings. These frozen fragments may also represent the primordial building blocks of the Uranian system, objects that failed to form into larger moons or were scattered during the planet's tilt event. Studying these objects could provide valuable clues about the early solar system's volatile architecture. Each orbit of these bodies serves as a silent record of eons gone by. As new observations refine our understanding of their orbits, the challenge of distinguishing these fragments from the crowded background of stars in Uranus's sky remains. However, each confirmed orbit adds to the intricate web of the planet's gravitational domain. These fragments may remain unseen by casual observers, but they are integral to Uranus's identity, serving as witnesses to cosmic upheaval while more visible systems grab our attention. Their quiet persistence is a reminder that much of the solar system is still hidden in plain sight. Next, we look at Makemake, one of the largest known dwarf planets in the Kuiper belt. Orbiting far beyond Neptune, in a region of icy remote worlds, Makemake offers fascinating insights due to the interplay between its unusual orbit and its shimmering surface, covered in frozen methane. Unlike Pluto, which has a thin atmosphere, Makemake seems to be airless, yet its surface shines with a brightness that suggests active surface chemistry. Despite its great distance from the Sun, its reflectivity rivals that of Erebus, indicating constant renewal of surface ices. Makemake follows an eccentric orbit tilted about 29 degrees relative to the ecliptic, taking over 300 Earth years to complete a single orbit around the Sun. At its closest approach, it lies about 38 AUs away from the Sun, 38 times the Earth-Sun distance. At its farthest, it reaches beyond 52 AU. This elongated orbit causes dramatic temperature swings that influence how methane and other volatile substances behave on its surface. Spectral analysis from Earth-based telescopes has confirmed the presence of solid methane, similar to that found on Pluto and Triton. However, the concentration and distribution of methane on Makemake is puzzling. There are patches or bands where the purity of methane is higher than in other areas, suggesting that sublimation and redeposition occur in cycles. Despite the absence of an atmosphere, this implies active surface chemistry driven by solar exposure. Unlike Pluto, Makemake does not display the visible haze layers that characterize its distant cousin. This raises questions about the role of temperature, solar radiation, and cosmic rays in shaping distant icy surfaces. In 2016, Makemake's moon, informally named MK2, was discovered, providing new opportunities to estimate the dwarf planet's mass and density. Early studies suggest that Makemake is less dense than Eris or Pluto, indicating a higher ice-to-rock ratio. This composition could explain the persistence of methane on the surface, without the significant loss of volatiles to space. The surprising absence of a substantial atmosphere on Makemake was confirmed only after stellar occultation data ruled out any significant envelope. Many astronomers had expected a thin nitrogen-methane atmosphere similar to Pluto's. Instead, Makemake appears to have lost most of its volatiles to space, or never developed the necessary gravity to retain them. Still, the frozen methane remains, clinging to the surface in a brilliant defiance of the vacuum. Makemake's eccentric orbit likely preserves much of its ancient history, offering a snapshot of the solar system's distant past. Studying this dwarf planet and its moon, Maki 2 provides crucial insights into the formation and evolution of icy bodies in the outer reaches of the solar system. As we learn more about these far-flung worlds, we gain a deeper understanding of the complex and ever-changing dynamics of our solar system. The position and tilt of Makemake suggest it was shaped during Neptune's early migration through the solar system. It was likely flung into its current path through gravitational interactions, making Makemake a remnant from a chaotic time in planetary formation. The surface of Makemake holds chemical clues to a more turbulent epoch, offering a snapshot of the early solar system. Spectroscopy of Makemake provides indirect insight into the distribution of energy in the Kuiper belt. Even at such extreme distances, sunlight continues to drive chemical reactions on these icy bodies. This makes Makemake an important natural laboratory for studying the chemistry of objects at the outer edges of the Sun's influence. While no spacecraft has yet visited Makemake, its brightness makes it an excellent target for telescopic observations. Its next perihelion will occur over a century from now, but until then, it remains a beacon of frozen methane, drifting in the distant cold of the outer solar system. It is a remote gem, glowing sharply against the vast darkness of space, carrying with it the secrets of our solar system's farthest reaches. Moving to Saturn's moon Rhea, long thought to be a geologically inactive body, new data from Cassini has challenged that assumption. The spacecraft's close-up images revealed an unexpected feature: dark markings scattered across Rhea's surface in highly geometric patterns. These shapes don't follow the randomness typical of natural formations. Instead, they appear in long linear arrangements that repeat at specific angles, suggesting some unknown underlying process. The origin of these markings remains one of the greatest unsolved mysteries in planetary science. The markings appear as dark streaks or blotches, running across both elevated and low terrain. Unlike the features produced by impact ejecta or cryovolcanism, these streaks don't radiate from a central source or follow the boundaries of the moon's topography. Instead, they run parallel or intersect at consistent angles, creating a grid-like effect that almost seems artificial, though no one believes they are. These features are mostly confined to Rhea's leading hemisphere, the side that faces forward in its orbit around Saturn. This asymmetry has led scientists to hypothesize that micrometeorite impacts, magnetospheric interactions, or surface charging might be involved. However, none of these explanations fully account for the sharp geometric precision of the patterns. One possible explanation is that particles from Saturn's magnetosphere strike Rhea's surface in organized belts, guided by the planet's magnetic field lines. These charged particles could chemically alter the ice in linear zones, darkening the surface in distinct patterns. However, Rhea's weak magnetic field raises questions about the accuracy of this model, as it would be unprecedented for such precise field geometry to form on a moon. Another theory suggests that these streaks are remnants of ancient fractures or tectonic shifts, which were later stained by material falling from orbit or exposed to space weathering. However, Rhea lacks the internal heat and geological activity seen on other moons like Enceladus or Europa. If these lines are ancient, they've been remarkably well preserved in a harsh dynamic environment. Cassini's images also showed no noticeable elevation difference between the streaks and the surrounding terrain, suggesting that the markings are superficial. They seem to be surface alterations rather than raised ridges or deep troughs. Their thinness and straightness further add to the mystery, indicating a delicate and precise process at work. Rhea's icy crust is unlikely to have formed or preserved such patterns on its own. Unlike Earth's geological layering or glacial activity, Rhea lacks weather, liquid flow, or plate tectonics. Whatever created these lines must have followed principles that are very different from anything we observe on Earth, likely driven by electromagnetic or particle-based forces. Despite their striking nature, these markings have not been studied in great detail since Cassini's flybys, as they were overshadowed by more dramatic features on moons like Titan and Enceladus. Yet, the geometric patterns on Rhea remain one of the solar system's most perplexing anomalies, quietly awaiting further exploration and understanding.